The evolution of classical physics. Physics is a branch of science that deals with the study of matter, energy, and the interactions between them. It is one of the oldest and most fundamental sciences, and its evolution has shaped our understanding of the world around us. Classical physics, also known as Newtonian physics, is named after Sir Isaac Newton, who revolutionized the field in the 17th century with his laws of motion and the law of universal gravitation. These laws provided a framework for understanding how objects move and interact in the natural world, and they remained the dominant explanation of physical phenomena for over 2 centuries. However, as scientific experimentation and technology advanced, classical physics was challenged by new observations and phenomena that could not be explained by its principles. The discovery of atomic structure and the behavior of subatomic particles, as well as the development of theories such as special and general relativity, forced physicists to re-evaluate their understanding of the world and develop a new branch of physics known as quantum mechanics. We will delve deeper into the history of classical physics, its major contributions, the challenges it faced, and its eventual evolution into the modern field of physics. Sir Isaac Newton was born in England in 1642 and is widely considered to be one of the greatest scientists of all time. He is most famous for his laws of motion and the law of universal gravitation, which he presented in his book Philosophiae Naturalis Principia Mathematica in 1687. These laws revolutionized the field of physics and provided a comprehensive explanation of how objects move and interact with one another in the natural world. Newton's first law, also known as the law of inertia, states that an object at rest will remain at rest and an object in motion will continue to move at a constant velocity unless acted upon by an external force. This law challenged the prevailing belief that a force was required to maintain motion and introduced the concept of mass as a property of an object. Newton's second law states that the acceleration of an object is proportional to the force applied to it and inversely proportional to its mass. This law provided a mathematical relationship between force, mass, and acceleration, and is still used in physics today. Newton's law of universal gravitation states that every object in the universe is attracted to every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This law provided a comprehensive explanation for the observed behavior of celestial bodies and was a major step forward in our understanding of the universe. Newton's laws of motion and the law of universal gravitation were a revolutionary step forward in the field of physics, providing a comprehensive explanation of how objects move and interact in the natural world. These laws remain a cornerstone of classical physics and continue to be studied and used in physics and engineering today. One of the biggest challenges to classical physics came from the discovery of atomic structure and the behavior of subatomic particles. The principles of classical physics, such as Newton's laws of motion, failed to accurately describe the behavior of these small particles, leading to the development of a new branch of physics known as quantum mechanics. Another challenge to classical physics came from the development of theories such as special and general relativity. These theories, developed by Albert Einstein, challenged our understanding of time, space, and gravity, and showed that classical physics was inadequate in explaining certain phenomena, such as the behavior of objects moving at high speeds. In addition to these challenges, classical physics also struggled to explain the observed behavior of electromagnetic radiation, such as light and X-rays. This led to the development of the theory of electromagnetism and the discovery of new particles, such as electrons, that would eventually become the building blocks of our modern understanding of the universe. As scientific experimentation and technology advanced, classical physics was challenged by new observations and phenomena that could not be explained by its principles. This led to the development of new branches of physics, such as quantum mechanics and electromagnetism, and the evolution of our understanding of the world. Classical physics has been incorporated into modern physics in several ways. For example, Newton's laws of motion are still widely used in engineering and physics to predict the motion of objects and to understand the behavior of systems. The principles of classical mechanics continue to be a fundamental part of physics, providing a foundation for more advanced theories and models. In addition, classical physics has also influenced the development of new theories and models. For example, classical mechanics and electromagnetic theory have been incorporated into quantum mechanics, leading to a better understanding of the behavior of subatomic particles. Similarly, classical physics has influenced the development of theories such as general relativity, which describe the behavior of objects and systems at the largest scales in the universe. Classical physics has also had a significant impact on the world outside of physics. For example, the principles of classical mechanics have been applied in engineering, leading to the development of technologies such as the steam engine and the automobile. Classical physics has also played a role in shaping our understanding of the natural world and our place in it. Classical physics continues to play an important role in modern physics, influencing the development of new theories and models and providing a foundation for our understanding of the world. The principles of classical physics continue to be widely used and studied, and have had a significant impact on the world outside of physics. We hope that this journey has been informative and thought-provoking, and that you have a better understanding of the challenges and achievements of classical physics and its impact on the world. As we come to the end of this video, we invite you to join us on our ongoing mission to understand the world and the universe around us. We would love for you to become a part of the Black Screen Science community by subscribing to our channel, liking this video, and leaving a comment with your thoughts and suggestions for future videos. Thank you for your time and attention, and we look forward to sharing our next journey with you. Until then, goodbye.